Curiosity is the essence of our existence. Gene Cernan, 11th and last human to walk the moon as of 2022. Space is bigger than we can imagine, and we have only just begun our exploration of it. What we know is minuscule, but it is growing. We are developing new ways to see and understand space every day. Today I will share with you the most fascinating way we can see distant planets, galaxies, and even dark matter. Gravitational lensing happens when a really big object, like a galaxy cluster, has such a huge mass that it bends the path of light around it towards us. In this image, it lays out the galaxy in the center as a lensing galaxy. It acts as the body of the mass that will bend the light waves that transmit what we see from the quasar behind it. Well, now I know what you may be wondering. What is a quasar? A quasar is a massive black hole that is surrounded by an accretion disk. The disk is constantly feeding off gas to the black hole, but the gas heats up and releases energy, creating a very bright light that rivals that of stars. We discovered quasars a long time ago due to radio telescopes, but we never actually saw them. The quasars were too far away for our current telescopes to be able to see them. But thanks to the effects of gravitational lensing, we were able to take photos of quasars. The 4 points of ball lights you're seeing are all one quasar. This happens during gravitational lensing. It's a phenomenon known as an Einstein ring. What happens to create this is when the heavy mass object that's curving the light is positioned at just the right angle that when it intercepts the quasar, light pulls the waves seemingly all around itself, creating either a solid ring or multiple instances of the object. Now this next clip is a clip about NASA catching the Einstein ring. It was aired by NBC News.
And the Hubble Space Telescope has captured what's called an Einstein ring. The image from the European Space Agency shows two galaxies that are billions of light years away from Earth, warping and deflecting light from an even farther galaxy behind them. The phenomenon is named after Albert Einstein, who first predicted that gravity could bend light.
There's 3 types of grav lensing. The first is strong lensing. The lens is a large mass and the deflection is large. The observer will see 2 or more separate images. Second is weak lensing. In weak lensing, the lens is a large mass, but the geometry of the mass is bad. The observer will see a mildly distorted image. Third is microlensing. The lens is a small mass. Even if the geometry is good, the observer will see a bright image with deflection, distortion, and multiple images overlaid. Strong lensing was used to establish the Hubble constant. With the change in images with the change in time, scientists were able to use the time delays and make the calculations needed to make the Hubble constant. Using weak lensing, clusters can be weighed. They use the average of a lensed galaxy in order to calculate information about the objects that the galaxy may be used to lens. This is dark matter. We can use microlensing to find the dark matter, as during microlensing, the object in the foreground becomes brighter for a time. Scientists use this in order to know whether something invisible is passing in front of the foreground. The image on the left is what we'd normally see when looking to the stars. The image on the right is the same photo but with a blue filter in order to help us see the dark matter. The dark hues of blue in the photo are the invisible matter that we aren't normally able to see. Gravitational lensing has also been used to back up big theories. Einstein's theory of general relativity has gravitational lensing as one of its key points, but he didn't know it just yet. He says that massive objects distort the fabric of space-time, the same way a bowling ball on a trampoline would stretch and warp the fabric around it. He's talking about gravitational lensing and how the massive object would distort the image. Einstein's early models look like the model above. He knew that the mass in the center at point M would create an indent in the space around it, causing the light coming off of point S to be warped toward the light coming at point 0. Part of a publication of collected papers of Albert Einstein. Einstein's conclusions initially was that the lens effect wouldn't be seen. He decided the improbability of it was too high for all the variables that needed to align for an event like this to occur. This is the first identification of a gravitational lens, which displays a clear Einstein cross. It was discovered in 1985. As time goes on, our photos get clearer and better, allowing us to see newer, further systems and use different types of grav lensing. The latest innovation in satellites and space imagery is the Hubble telescope. It's a powerful telescope designed to see very far into space and get detailed images of things that we could have only dreamed of seeing before. This image shows how the Hubble telescope sees gravitational lensing. The telescope will take in the distorted light rays that are being bent around the galaxy cluster and will piece that together to make images of distant galaxies. We have visited the origins of grav lensing. We've seen notes and ideas before it was confirmed. Grav lensing is an integral part of how we see and discover the vast openness of space. This image revisits what the model of grav lensing looks like. Many people have never heard of gravitational lensing and may never feel the need to know, but I believe it's important to know. Gravlensing shows how different aspects of physics is applied naturally to the world around us. Light is waves and moves as we know through physics. Mass can apply a pull on the waves around it. It's a coalescence of important topics that is basic, but allows for huge leaps of knowledge to be made. Gravlensing is more than important. It's a beautiful sight to behold. The varying lenses we can see through can show us wonders of light that we are unable to replicate or dream of. Each of the photos of space I've used were picked because of the beauty of space. It's dark and mysterious and has an air of awe surrounding it. Gravitational lensing helps us understand a distant frontier which we have no business reaching. A tool so simple that man was able to identify it before current technology. We are able to see the world of the stars and the unseen. Gravitational lensing allows us to see galaxies, clusters, and matter that's invisible to our naked eye.